Okay, so yesterday we had kind of talked about some other cases with these equations that we're trying to solve for, and we did talk a little bit again about factoring, which is something that we've done already. And we also then got into the square roots, like the radicals and how you deal with that. So similar to what we just did on our bell ringer. I've got a couple other forms to kind of talk to you guys about today, just so that if you see these, you kind of know what to do. The first thing we're going to talk about is rational exponents. Rational, remember, means fraction. So we're talking about fractions that are in our exponents. You can even see down here on these problems how we've got like an x to the 4/5, an x to the 3/2. We've seen something like this before, but what I might want to do instead is think about this as like a radical form so that I can maybe get the fraction to go away. So it's almost going to look like we're working backwards a little bit because we're going to make it become radical form. But the reason why we do that is because it's going to be easier to get rid of the radical, and then you won't have a fraction anymore, and you won't have a square root anymore, and you're just working with like regular terms like we've been used to seeing. So in the past, when you guys saw things like x to the 3/7, let's just say, you were maybe told last year in Algebra 2 that you could rewrite this and the x goes like underneath the radical sign, and then you take the 3 and the 7 and you have to put them in the right spot. The top number is always what goes underneath the radical sign with the letter. So the 3 is going to go underneath the square root sign. And then that 7 is telling you what the index or like what that root sign would be working with. So the 7 is going to go in that little corner by the square root sign. So if I had even just regular x to the 1/2 power, this is really how we get the square root of x, because there'd be a 1 here and there'd be a little 2 in that corner. But most of the time we would just write that as the square root of x. But that is where it came from, is we had a fraction as our exponent and then we rewrote it as a radical sign. But so when they start to throw in other numbers at you, now you kind of know how to rewrite it so that you can put the correct number under the square root sign and the other number on the outside of the square root sign. So for example, on this first one, the first thing I'm going to do before I even rewrite anything is I'm going to move this 30 over to the other side. So I'm going to add 30. And so it says now 3 x to the 4/5 equals 30. One other thing I want to do is just get rid of that 3 in front of the x. So I'm going to divide both sides by 3. So then this now says x to the 4/5. And what would be 30 divided by 3? 10, right? So now what we're going to do is rewrite the left-hand side. So I'm going to change this to a radical sign. I'm going to put x underneath. What number goes underneath with the x? 4 does. And so 5 has to go on the outside. And so we have that equal to 10 now. Okay, so we were kind of making some progress. We're getting x by itself. Now we've kind of switched it back to the radicals like we talked about yesterday. But how can I get rid of that radical sign? What should I raise both sides to get rid of that radical? To a 5, because that outside number is a 5 this time. You know, on our bell ringer, we squared it because it was a regular square root. This time there's a 5. So I'm going to raise both sides to the 5th power. Okay, and then underneath here, that just becomes x to the 4th. What would be 10 to the 5th power?
100,000.
Just a 1 with 5 zeros, because anytime you raise 10 to a power, that tells you how many zeros the number is going to have. And then what would you do?
Do the 4, whatever it's called.
The root sign?
Yeah.
Yeah, we're going to do the 4th root of both sides now, because that's going to finally get me just my x. Can we take the 4th root? You guys have a calculator? Can you try that?
It's a decimal.
It's a decimal. So what'd you get for your decimal?
17.78.
If you does your calculator reduce the radical on that one for you or no?
What do you mean?
Like do you have it in the mode where it would just spit out a reduced radical for you, or is it
It
only?
just went straight to decimal.
It went straight to decimal. So that must mean then that there isn't anything that would go into that as far as the fourth root goes. So even if you left it up here, that would probably be correct as well. Because like if your calculator's in that right mode, if we had like the square root of something, it'll sometimes just do it for you. But if it's not going to do that, that means it's not possible. Okay, so I know those problems kind of feel a little bit like we're going back and forth. Like we made some progress by solving for x, then we switched it to a radical, and then we had to get rid of the radical, and then we had to square root it again. Like you're kind of going back and forth between those, but it's mainly because you're working with those exponents. Okay, why don't you guys go ahead and try the second one? It's the same idea. I'll give you guys a chance to try one on your own here. Okay, I've kind of got it started here. I started by isolating the x term. Now I'm going to rewrite this as a radical. So x goes underneath the radical sign. What number did you guys put underneath it? 3. And then there's technically a 2 there. I'm not going to write it though, because if it's a regular square root, there's always a 2 there. So I'm not going to really worry about putting that in there. And then that equals 5. Then I want to get rid of that square root, so I'm going to square both sides. So now it says x to the third equals 25. And then what'd you guys do to finish it? Cube root it. And can we cube root 25? What's like your approximate answer? Okay. I don't know if we can cube root 25, so if you want to keep it there, that's fine. Does anyone have the decimal though? 2.9? Any questions on those ones with the radicals and the rational exponents there? Okay, so we're going to kind of go back to the quadratic form, but these ones maybe aren't going to look like the quadratics that we've seen in the past where you had x squared, x, and then a number. If something still has 3 terms and that leading term, so the exponent of the leading term, is double of the term in the middle, then it's technically considered quadratic. So on this one, it says x to the 6 plus 2x to the third minus 3 equals 0. That's technically quadratic because 6 is double of the 3. So another example, if you had like x to the 10th power plus x to the 5th power plus 1, let's just say, that's technically in quadratic form again because 10 is double of the 5. So as long as that relationship is happening with those exponents, it's in your quadratic form. It just looks a little bit different than what we are used to seeing. So because I know it's quadratic, that means that I can try to factor it. I could try to use quadratic formula. I could try to use completing the square in order to solve this. Most of the time when I'm going to do these, I'm going to try to factor first, just because factoring is usually faster than the other methods. Like quadratic formula is great, but it's a little bit time consuming because you have to plug in all the pieces and do all the simplifying. Instead, I'm going to try to think about, could I factor this? So could I multiply to a -3 and add to a 2? What numbers do that?
-3 and -1.
Okay. So then we're going to do what we did before. We're going to split this into 2 parentheses because we found those numbers, so we're able to kind of shortcut our way here. Now the x to the 6th power, that's that leading term. You have to think about when you had x squared, we would split it. So it would be x and x. How would you split x to the 6th power? X to the 3rd. So each one gets x to the 3rd, x to the 3rd, and then your numbers, +3 and -1. Then we're going to set each of those equal to 0, and we're going to solve them. So that first one I would subtract 3, so I have x to the 3rd equals a -3. Then, just like what we were doing up above, we're going to cube root both sides to get rid of the exponent. And so that's just going to be x equals the cube root of -3. And it's okay if we have a negative underneath an odd root. Really, it only has an issue when there's the negative underneath an even root. That's when your I is going to show up. For the other side, I would add 1. So I have x to the 3rd equals 1. If I cube root this side, what do I get? What number times itself 3 times is 1?
1.
Just 1. So those are your 2 answers. Okay, so the next one, is it quadratic? Does the first term exponent double the middle term's exponent? Yep, so we should be able to do what we just did before. Let's try to factor this one again. Can you guys think of 2 numbers that multiply to 6, add to a -5? You don't have to write out that chart. Like if you know that, you can do that mentally. I'm just putting it there so you know where we're getting these numbers from. So now let's rewrite this. How would I split that x to the 4th power? The last one was x to the 6th, and we said x to the 3rd, x to the 3rd. So what would this one split as? Okay, and then -3 minus 2. We set those both equal to 0. On this side, you're going to add 3. So you have x squared equals 3. Then what are you going to do? Square root. Can we square root 3? No. So one answer is the square root of 3, plus or minus technically. On the other side, we would add 2. So if x squared equals 2, can I square root 2? No. So I'm just going to add on plus or minus square root of 2. All right. If you guys go to the next page, we've got one more special case to talk about before we get into an application problem. So the last special case I want to cover with you guys is something called the absolute value one. We've talked a little bit about absolute value. You had to graph something that had absolute value in the past. So remember, an absolute value graph looks like a V. Okay, so that would be an example. It's still linear, but it always makes a V shape. All absolute value graphs do that. Sometimes they're facing up, sometimes they're facing down. It just kind of depends. Now, when we think about absolute value, you're talking about like distance from 0. So anything inside of absolute value bars is always positive because we can't have a negative distance. Okay, you can't measure distance negatively. You can't get negative amount of flooring for a room, you can't drive negative miles. Like those things don't happen. So when we think about absolute value, whatever's inside of those bars is always going to become positive. Now, because of that, if you put in a -5 in absolute value or you put a +5 in absolute value, you get 5 both times. But there were two potential options that would have created that answer. So when you set up an absolute value equation, there's actually two routes that you have to take. The first one is exactly how it appears. You just take everything, but you drop the absolute value bars. So 2x minus 1, you set that equal to 5. Let's go ahead and solve this. What would you guys do first? So I have 2x equals 6, and then what? And we get x equals 3, okay? That's one answer. But we have to think about, well, what if the opposite sign had been put into the absolute value bars and then they solved it? So in that case, everything looks pretty much the same except for one little piece. You're still going to bring down 2x minus 1. No absolute value bars. But instead of saying equals 5, we're going to say equals -5. Because again, I'm thinking about the opposite side of things if I had put in the opposite sign. Okay, what would you guys do first here? Still add 1. The solving really does not look any different. It's just your number is going to be different over here. Because when I add 1 to a -5, I get -4. And then what? And we get -2. So absolute value equation should have two answers to them. Similar to like a quadratic has two answers. Questions on that? How to set up those absolute value ones? Make sure you do both sides. That's probably the one mistake I see is kids will do one side, but they'll forget to do the other one. So make sure you're thinking about setting up two equations. Okay, last problem we have here. We've got this formula, h equals -2.3 times the square root of I plus 67.6. This models weekly television viewing time. H represents your hours. Annual income, I, is in thousands of dollars. We want to figure out what is the annual income that corresponds to 33.1 hours per week of watching TV. So we're going to put in the hours that they're giving me for H. So that 33.1 goes in for H at the beginning. And we're going to set that equal to the rest of the formula. And I need to solve for I because they're asking me for the income. So think about what we were doing before. We want to try to get that radical where the variable is kind of by itself. So what should I move over first?
67.6.
Okay, so I'm going to subtract that. So what would be 33.1 minus 67.6? Okay, and that still equals -2.3 square root of I. Then what should I do? Okay, -34.5 divided by -2.3 is 15. So now I've got 15 equals the square root of I. How do I get rid of that square root sign? Square it. So I equals what? 225. Okay, now think about this for a second here. We're talking about annual income. So is someone going to make $225 in a whole year? Does that make sense? 1,000. Because up here in the problem it said annual income I is in thousands of dollars. So we need to add a couple of zeros to our answer there to make it make sense. Questions about that problem?